So, welcome everyone to the last but hopefully not least talk of the track for today. I want to start with just a quick introduction of myself. My name is Julian Trommer and I am currently a PhD student at the University of Augsburg in the chair of mechatronics. And, sliding off. There we go. Okay. And I want to talk about our package MeshGraphNets.jl today and our adaptation of that graph neural networks-based methods to a NeuralODE. And for starters, I want to show you one of the use cases that was in the original paper of MeshGraphNets, which was published by Google DeepMind. And this is just the example of an incompressible fluid dynamics. So you can see just fluid flowing from the left to the right around that white cylinder. And I just want to show you the results of a ground truth versus the prediction. And you always see these kind of fancy animations and you think, okay, well, that looks pretty good. But the questions that I ask myself is, how good actually are these results? How good is the accuracy? And how can we use this method if we want to implement it in an industrial use case where we have more stringent requirements to precision? And that is why we developed our package. So I'll just start with a quick introduction. So what exactly are MeshGraphNets? So MeshGraphNets are a graph neural network. So at the base layer, it's just a neural network approach. And the idea is that you have a spatially distributed system. So for example, the example that I showed at the beginning is a spatially distributed domain. And you can represent that domain with a mesh, as you saw, and you can translate that into a graph. And like a NeuralODE, you substitute the differential equations with a neural network to speed up the process mainly. So these are designed for surrogate models to speed up the process of simulation. You then have the quantities of interest in the introductory example, the velocity in x direction at the nodes of your graph. And you can interpret it as the mesh or the graph is used to propagate these node features along the edges of the mesh in order to influence nodes further down the graph. But I will dive into the detail on the next slides where I give a quick introduction of how these MeshGraphNets actually work. So they are based on the DeepMind called it encode process decode architecture. So in the first step, the encode process is just there to translate our features from the physical space to the latent space. And that is what you have then in the graph. I will update the graph on the right so you can follow along. So there you have the node features, as I mentioned, and the edge features. This is just to have the relative vectors and their length. So you have the relation also as an input of the system. Then in the first step, you update these edge features according to their connecting node features. So you just take an edge, you take the nodes that are connected to the edge, and you accumulate these features and push it to a fully connected neural network. And in the second step, you take these updated edge features, and if you look at the circled nodes, you take all the incoming edges and accumulate these edge features that were calculated in the previous step and update the node feature of that node. And you do that for every node in the graph. It's just for a representation purpose. That I drew the arrows to only one node, but you do that for all the nodes simultaneously. And then you can repeat these steps. So this is the so-called process stage with the message passing steps. this is just a hyperparameter of the system, so you can interpret the message passing steps, the number of message passing steps, and how you want to influence the nodes further on the line. So the more message passing steps you do, you can imagine the further down the graph you're influencing nodes in the same time step if you have more message passing steps. And in the last step for the decode stage, this is where we just do the reverse of the encode stage. So we want to get back from our latent space to our physical space, so we can get to our physical quantities of interest. And then we can calculate our next state. It is important here to mention that in the original implementation of MeshGraphNets, there was a fixed time step learned into the system. So the result of the system was not the state derivative, but the state itself. So that was one of the adjustments that we made that had to be done in order to include it as a NeuralODE, so that the system as an output has our state derivatives, not our states. So, just a quick introduction, since we're at the SciML track, I'm pretty sure most of you know what NeuralODEs are, but just as a quick introduction for NeuralODEs, they're basically just you have a neural network that you use instead of your physical equations, or you calculate your next or your state derivative on the neural network, and you can use a numerical solver, so the network doesn't have to learn all the numerical the stuff the numerical solver has to do, and you make the learning task way easier, and can use different solvers for different applications that you have, which we'll see later. Now the idea of the package is that instead of just a normal neural network, we plug in the MeshGraphNets into the block shown here. And that means we can not only have the machine learning aspect of the approximation, but we can also integrate the physical knowledge that I previously showed because of the graph structure that we incorporate into our system, and can thus incorporate the knowledge, the physical knowledge, into a system to get a better result at the end. And this is basically what is shown here. So now we can use the numerical solver to get the next state of our system, and that means we can, for example, use a solver-based training, so we not only have to use a derivative-based learning approach, but we can also incorporate a solver into our learning process, and we can also use different solvers. For example, if you want to use adaptive time stepping, that's possible, or based on your requirements, maybe you want to use an implicit solver if you have a stiff system. That's all possible in this design. Okay, so for the industrial application that I want to present today, I have a quick graphic to show. So the underlying model that we use is the model of a hydraulic brake system, as you can see here. And the model is basically comprised of, the most important part is the pipe in the middle, as you can see with a red dot at the top. And that is where the most of the calculations are, because the idea is in this model is just a simplified version, but you have a pressure wave at the left. These Pac-Man looking guys are just boundary conditions. We can ignore them for now. And you initiate a pressure wave into our pipe, and this causes the wave to travel across the pipe, and the pipe itself is, like we've already seen in a talk before, is just a spatially discretized 1D model, and consisting in this case of 115 cells. And we have further look at this. In our case, if we want to incorporate it into our MeshGraphNets.jl library, it's pretty convenient because we have the necessary spatially distributed domain here, so we can just set our nodes into the edge and into the centers of our cells. Cells more or less because we're 1D, but let's keep it at that, and connect them and have a one-dimensional graph. And we can use our approach. The representation for 5 cells is just here for easier understanding. Like I mentioned previously, in this case we had 150 cells. It's just for easier understanding. One slight adjustment that we did when I previously mentioned the boundary conditions, to help our network a bit, we can take advantage of the MeshGraphNet structures and try to enforce some boundary conditions into our system. So that is what we did here. So you can see on the left where the input of our system is, like I mentioned, where the pressure wave is initiated. We have the pressure as a constant input because that is what we tell our system what the input is. And on the other side, we can set our mass flow to 0 because we want to tell our system, okay, there is no flow going here because the pipe is closed there. So if the pressure wave travels through the pipe and collides at the end, it is reflected back. That is basically what this tries to tell the system. So now for some training and evaluation data, like I previously mentioned, we had 150 cells in our system, which consists of pressure and mass flow. And on the right side, there are just some plots that show you one example trajectory of our system. Here, I plotted the wave for cell 25. Here's for 75 and for 125. This is just for the later plots that I show you, that we can have a rough estimate so that we have the start of the pipe, the middle of the pipe, and further down the end of the pipe. So we get a nice visualization of the travel of the pressure wave. Yeah, like mentioned, the same goes for the mass flow. So we have mass flows also for the 3 cells that I just mentioned. And our input data to generate our data, we just use the jumps in the pressure wave of 0.8 to 2.1 bars. So if you start at 1 bar, in this case, and we just jump to 1.8 and 2.2 bar, and this was our data, and this was then split into training, test, and validation data, and everything that you see in this presentation was done with a TZ5. So the training as well as the evaluation of the system was just was all done with a TZ5 from differential equations. So let's look at the results. At the first step, what we did was we tried to train our system with just the derivative-based method. So at the first glance, we took out the solver, and we wanted to see how well does the system perform if we are just giving it the derivatives of the data. This is what you can see here in blue in relation to the ground truth data that you can see in orange. And you can see that, well, it's not bad. So the system kind of gets the idea of the pressure wave that travels through the pipe. But we definitely could be better, could do better, especially if we look at the start of our system. This is just zoomed in on the first 2 jumps, or the first 2 bumps in the slide that I showed previously. And here we can see, well, there's definitely some deviation at the start that we don't want. So what we did next was we tried our solver training, because now in our architecture we can do that. And what you can see here is when we trained our system with the solver in yellow, so it's a much nicer fit. And it is important to mention here that we trained our solver only on this part, so only from 0 to 0.085 seconds. And then what we wanted to see was how well does our system extrapolate if we then look at the trajectory that I showed before, so the 0.41 second. This is what is shown here. So this is just the comparison of the derivative-based training in blue again, and the training that we did with the solvers. So the reason why there's a plus at the bottom right is because we first trained with the derivative-based training and then on top trained with the solver-based training afterwards. And what we can see here is, especially at the middle cell and the cell further down the pipe, the solution is pretty good. So we can quite accurately match the ground truth data. At the start, you can see a bit of a deviation. But as you can see here, if we remember what we trained our model on, mainly the first two bumps here in the ground truth data, you can see up until there it's better, and then it just loses the accuracy further down the plot. But that is quite a good result for just training on the first part of the trajectory. The same also applies for the mass flow. I just showed you only pressure waves for convenience sake, but here just so you know, the system also predicted our mass flow, and here you can see there's the prediction with our solver-based training is quite a lot better than the prediction of our solely derivative-based training, but with the same error as I showed previously in the pressure. But here it's on the other side, so on cell further down the line, the mass flow is better in the first two bumps, but gets a bit worse afterwards. But also it has a pretty good approximation or extrapolation of the trajectory that it didn't see. So now to quantify a bit what we saw right here. This is just the cumulative mean squared error of our test data. So what I showed you was all test data, so there was nothing of these pressure jumps was seen by the surrogate model. And this is the cumulative MSE over the whole test data. And as you can see here, the numbers also speak for the approach with the derivative plus solver-based training, that we have a better solution. Now I want to give a quick outlook to what is also possible, because this was a very simple use case. If you know a bit about the model, it's not that difficult. So the main goal of the MeshGraphNets that we can simulate our system faster was not really given, because the system itself is not too complex, so we were around the same simulation time, around about 30 seconds. That is why I want to show you a quick example of another industrial use case that we implemented our MeshGraphNets for, and that is a cabin model. So this is just a two-dimensional slice through a vehicle cabin, and you can kind of identify the seats. And similar to the pipe, it's also discretized in these finite volume cells, but this time we're in three-dimensional space, not only one-dimensional space. So we up the dimensions of our system, which is possible because we just have to define our mesh or our graph on three-dimensional plane instead of a one-dimensional one. And for the results that I want to show you, we're focusing on just that type of cell, just because the system has 400 cells, and I don't think anyone wants to see 400 plots of solutions. And the reason why I chose this cell is because that is one of the more important cells for the user of this model, because that directly correlates to the comfort of our driver, how hot or how cold he feels. Like I just mentioned, we can then use a three-dimensional mesh to apply our method. And for our data that we are using heat-up cycles. So the data consists of actively heating up the vehicle cabin through a HVAC system. So we're actively blowing hot air into our system. And the main goal is to try to predict the temperature of the cells. So what we see here are similar results to the hydraulic brake pipe that we've seen before. You can see here in orange is our ground truth data. The reason why we have a green strip around the ground truth data is because that was one of the requirements that we had. We should not deviate from a 1 Kelvin plus minus from the ground truth data. This is why the green plot is there. And as you can see, if we just use the solely derivative-based training in blue, the solution is not in the green area of the plot, which is not what we wanted. But if we also try our approach with solver-based training, you can see in yellow, then we're matching our ground truth data actually quite good. And that is exactly the results that we were looking for. And since I already spoke, now we have a way more complex model than before. So the numbers are a bit more interesting. If we look at the simulation time and the cumulative mean squared error, so the original model for our simulation was around 260 seconds. And with our surrogate model with MeshGraphNets, we only had a 30 seconds simulation time, which is a big improvement. And like previously in the pipe for the hydraulic brake, we also show that oops, that is my mistake. I messed up the numbers. They should be the other way around. The derivative-based training is, of course, the one with the 4.3 mean squared error, and the derivative plus solver-based training is the one with 0.596. So just a little mix-up. So for our conclusions, what we did was we formulated the MeshGraphNets network as a NeuralODE to make it possible to use these kind of solver-based trainings in evaluation methods, and we showed that this is also the way to improve our results of our solution. And we showed 2 applications of our industrial use cases where we applied the method and had results that were very good. Our next steps are we want to try and make use of a more complex hydraulic brake model because, like I mentioned, this is a quite simple model, but the reality is not like that. The models for hydraulic brakes are quite a lot more complex. And without going into detail, we want to implement the approach for the more complex models and see if we can achieve similar results to our cabin model, which was also quite complex. And this also means that the pipe model can be extended, because one of the main advantages, since we have these graph-like structures in MeshGraphNets, we can try to expand our graph if we change our spatial domain. So for example, if we make our pipe a bit longer, if we change the layout of our vehicle cabin, then we do not have to retrain our system, because we are not learning a global solution, so to say, but the local relations between the nodes and the features. So it is possible to evaluate our system without retraining it. And that just falls under the last point that is written here, which is the further development of the package, which you can find under MeshGraphNets.jl, so the release package on the QR code. We're always welcome for issues or PR if you try to use it, and maybe if you like it, leave a star, that would be great. And with that, I conclude my talk, and I'm glad if anyone asks any questions.
Maybe a technical question. Why do you use Ceturas? Because I think your problem, at least for higher number of nodes, will be stiff, and Ceturas is a non-stiff solver, right?
Yes, that is correct. We tried a lot of different solvers, and it is always a trade-off between the training times and what you try to achieve. So the training process with implicit solvers is not really possible in the current ecosystem, because if you try to use implicit solvers on the GPU with Zygote, there's such a huge model, because it has a lot of parameters, then it gets quite tricky. So for the training, it's not really feasible. That's why the solver got used. But what we saw in the simulation times is that although the DZ5 is an explicit solver, because of the adaptive time stepping, it was able to match the data quite well, although it's not a stiff solver.
Okay, thank you.
Is it possible to extend this to, let's say, different coordinates than the nodes in the mesh that you have now? Because, for example, the first example, or the first break, I think it was, seemed to be quite low dimensional in dynamics.
The structure of the mesh you can always adapt, because, like I mentioned, the solution that, or the system that I learned is not the global one but a local one. So changes in the structure are always possible. It's just a matter of, are the results still good enough for what you need or what you want?
Just a question on how would you define the mesh typically for quite complex 3D geometry?
In this case, it is, well, most of the times it is given by what you can actually get from the data. So for example, for the cabin model, our only approach was, like I showed, where we used the center of our cubic cells as our nodes and connected them, because these were the only points where we could sample of quantity of interest in the original model. So that is one aspect that you're limited to. If you have more freedom there, so you can more arbitrarily choose, then there's also the possibility of hyperparameter tuning your mesh layouts, or for example, what in the original paper was dynamically remeshing if the accuracy is not good enough. But in this case, we were just limited to what you can get from the model. And that is most often not the case, that you're limited to such things.